हेलो स्टूडेंट्स, आज हम मैकेनिक्स के ऊपर एक बेहद ही कॉन्सेप्चुअल क्वेश्चन को करने की कोशिश करेंगे। यह है हमारा आज का क्वेश्चन। द क्वेश्चन सेज इन द फिगर शोन द कार्ट ऑफ मास 6m is initially at rest. This is a cart, it is having a mass of 6m, it is initially at rest. A particle of mass m is attached to the end of the light rod which can rotate freely about A. इस कार्ट के अंदर में एक रॉड है, इस पॉइंट ए पे फिक्स्ड है, कार्ट की सीलिंग से फिक्स्ड है। पॉइंट ए के अबाउट में रॉड ऐसे रोटेट हो सकता है। ये लाइट रॉड है, रॉड का मास नेग्लिजिबल है, इसका ये एंड फिक्स्ड है और दूसरे एंड पे एक पार्टिकल बंधा है मास m का। द रॉड इज रिलीज फ्रॉम रेस्ट इन हॉरिजॉन्टल पोजीशन शोन। इनिशियली रॉड को इस पोजीशन में रखा गया है, जैसा कि अभी आप डायग्राम में देख रहे हैं। इस पोजीशन से हमने रॉड को छोड़ दिया। नेचुरली ये पार्टिकल ऐसा स्विंग करेगा और क्वेश्चन में आपसे दो बातें पूछी गई हैं। फाइंड द फोर्स अप्लाइड बाय द कार्ट ऑन द फ्लोर इमीडिएटली आफ्टर द रिलीज। जैसे ही हमने इस रॉड को यहां से रिलीज किया, रिलीज करने के तुरंत बाद ये कार्ट फ्लोर पे कितना फोर्स लगा रही है ये बताना है। एंड देन फाइंड द फोर्स अप्लाइड बाय द कार्ट ऑन द फ्लोर एट द इंस्टेंट रॉड बिकम्स वर्टिकल। और जिस समय रॉड वर्टिकल हो गई उस समय पे कार्ट फ्लोर के ऊपर या फ्लोर कार्ट के ऊपर कितना फोर्स लगा रहा, हमें ये बताना है। शायद एक चीज यहां नहीं लिखी, मैं बता दूं आपको कि दिस सरफेस इज स्मूथ, देयर इज नो फ्रिक्शन। तो एक कार्ट है 6m मास का, उसके अंदर m मास का एक पार्टिकल एक मासलेस रॉड से अटैच किया गया ऐसा, और ये एक पेंडुलम की तरह ऐसे स्विंग कर सकता है। स्ट्रिंग नहीं है, रॉड है। इसको यहां से छोड़ के मैं हट गया। छोड़ने के तुरंत बाद ये जो फ्लोर है ये कार्ट पे कितना फोर्स लगा रही है, पहला क्वेश्चन। दूसरा क्वेश्चन, जब ये रॉड वर्टिकल हो गई उस समय ये फ्लोर कार्ट पे कितना फोर्स अप्लाई कर रही है। तो आप सभी चाहें तो इस क्वेश्चन को खुद से ट्राई करें। बच्चों, यहां जो सबसे पहली अहम बात आपको समझनी है वो कुछ ऐसी है। अगर ये रॉड मासलेस है, मासलेस, तो ये किसी चीज के ऊपर ट्रांसवर्स फोर्स नहीं लगा सकती। जैसे एक स्ट्रिंग से मैं अगर कहूं कि इस स्ट्रिंग से इस पार्टिकल के ऊपर ऐसा फोर्स लगाना है, दैट इज नॉट पॉसिबल। स्ट्रिंग कैन ओनली एक्सर्ट फोर्स अलोंग इट्स ओन लेंथ। वही चीज ट्रू है एक मासलेस रॉड के लिए भी। If the rod is massless, it cannot exert a transverse force on the particle. It cannot exert a force like this. It can pull, it can push. This is one difference when you compare it to a string. A string can only pull, but if it is a rod, then it can push this particle if needed. It can pull this particle if needed, but it cannot apply a force that is perpendicular to length of the rod. Why am I saying so? Suppose in this case only, let us assume for a time being that rod is applying an upward force on the particle. Just assume that rod is applying an upward force on the particle, then particle must be applying equal force on the rod in opposite direction. So particle is applying a vertically downward force on the rod, but the rod is massless, isn't it? So if the rod is massless, net force on it must always be zero, otherwise its acceleration will become infinite. So the net force on the rod must be zero. It simply means that the hinge, the wall to which this rod is connected, that is also applying a force on the rod in this direction. So if the particle is pushing on the rod like this, the wall or the hinge, whatever you call it, it is also applying, the support is also applying a force on the rod in opposite direction, so that net force on the rod is zero. But these two pair of forces make a couple basically. So there is a non-zero torque on the rod. Again the same problem. If the rod is massless, which means it does not have inertia, then it cannot have any force acting on it. It cannot have any torque acting on it. Because if there is some torque on the rod, it will mean that it will have an infinite angular acceleration, which is again not going to happen. So if a body is massless, you cannot apply a net force on it, you cannot apply a net torque on it, because it has got no inertia, right? So this particular rod cannot experience a torque, which means particle cannot exert a force like this, which means that rod cannot exert a force on the particle like this. So, perpendicular to length of the rod, rod will not exert any force on the particle. That is the first and foremost thing that you need to understand. Next, as soon as this particle is released, as soon as this system is released, this thing, this thing, I mean the pendulum is going to swing, no doubt about it. But as soon as you release this, this is point A, this particle is experiencing a downward force mg, isn't it? The rod cannot apply a vertical force on it right now. So, in vertical direction, the acceleration of the particle has to be g. If you just isolate the particle and think about it, it is experiencing a vertical force mg. So, its acceleration must be g downward, isn't it? It is. So, right now when you release the particle, immediately after the release, particle is not having any speed. Immediately after the release, particle is not having any speed. So, there is no question of any radial acceleration also. अगर पार्टिकल के पास कोई स्पीड रही होती तो रेडियल डायरेक्शन में एक एक्सेलरेशन होता, पर अभी पार्टिकल को छोड़ा, इसकी कोई स्पीड नहीं है, तो इधर भी कोई एक्सेलरेशन नहीं है. तो फैक्ट ये है कि जैसे ही पार्टिकल को छोड़ा है, रॉड भी अभी पार्टिकल पे कोई फोर्स नहीं अप्लाई कर रही. देयर इज नो टेंशन. द ओनली फोर्स दैट द पार्टिकल इज एक्सपीरियंसिंग इज mg and therefore its acceleration is g downward. Okay, in simple language it means that there is no interaction between the rod and the particle as such. So यहाँ रॉड हिंज के ऊपर कोई फोर्स नहीं लगा रही है, पार्टिकल रॉड पे, रॉड पार्टिकल पे, रॉड हिंज पे कोई फोर्स नहीं लगा रहा है. So if you just isolate this cart, just think about the cart. ये जो कार्ट है इसके बारे में अगर हम सिर्फ सोचते हैं तो इस कार्ट का वेट 6 mg नीचे एक्ट कर रहा है. 6 m इसका मास दिया गया है क्वेश्चन में, और सिर्फ कार्ट के बारे में सोच रहा हूं. फॉरगेट अबाउट रॉड एंड पार्टिकल. रॉड एंड पार्टिकल आर सेपरेट थिंग. आई एम थिंकिंग अबाउट द कार्ट. So this rod particle system is not exerting any force on the cart right now. Immediately after the release, there is no force. So obviously this floor is applying a normal force which is equal to 6 mg, because there cannot be any vertical acceleration of the cart, right? So the normal force applied by the floor on the cart immediately after the particle is released is 6 mg. I hope you have understood the first part of the question. Find the force applied by the cart on the floor immediately after the release. It is 6 mg. Now the second question says, find the force applied by the cart on the floor at the instant the rod becomes vertical. Okay. So let me again erase this. When the rod becomes vertical like this, the bob, the particle, at this very moment is moving horizontally, isn't it? It is going this way with some speed, and the cart must be going in this direction at the same instant. The physical reason for motion of cart is that as this pendulum swings down, जैसे जैसे ये पेंडुलम नीचे की तरफ ऐसे स्विंग करता है, इसके पास एक स्पीड रफ्तार आ गई, तो रॉड में टेंशन होगा. देयर विल बी रेडियल एक्सेलरेशन. रॉड में टेंशन होगा तो रॉड का टेंशन कार्ट को हॉरिजॉन्टल डायरेक्शन में पुल करेगा. टेंशन का एक हॉरिजॉन्टल कंपोनेंट है, सो ऑब्वियसली कार्ट विल मूव इन दिस डायरेक्शन. सो दिस इज द फिजिकल कॉज. दैट मींस कार्ट इज एक्सपीरियंसिंग अ हॉरिजॉन्टल फोर्स, देयरफॉर इट विल मूव इन हॉरिजॉन्टल डायरेक्शन. और वैसे आप जो समझते हैं कि इस सिस्टम का सेंटर ऑफ मास हॉरिजॉन्टल डायरेक्शन में डिस्प्लेस नहीं होगा, तो ये पेंडुलम बॉब जो उधर गया तो कार्ट को इधर आना पड़ेगा. ऑल दोज थिंग्स आर राइट, नो डाउट अबाउट इट. नाउ let me assume that the velocity of this bob at this instant is v, and velocity of the cart is u in this direction. So I can write this equation. What I am saying, at this very moment the velocity of the bob is v and velocity of the cart is u. Mind you, I am in the reference frame of ground only. My observer is standing on ground, and that observer is seeing that this particular object, this particular particle is moving with velocity v horizontally, and at that instant the whole cart is moving with velocity u. I remind you once again, these two are velocities with respect to ground. So obviously, when I release this whole system, now I am talking of the whole system was not experiencing any horizontal force. So in horizontal direction, the momentum was 0, it will always be 0. When I released it, the momentum of the system is 0. When this rod swings to this position, at that instant also momentum must be 0. So this mass m is moving with velocity v in this direction, momentum is mv. At the same instant, this 6m mass is moving with velocity u in this direction. So mv and 6mu must be equal, so that the net momentum remains 0. So conservation of momentum tells you that v is equal to 6u. I repeat once again, v is velocity of the bob in ground reference frame, u is velocity of the cart in ground reference frame. Now the entire mechanical energy of the system must also be conserved, and only gravitational force is performing work, right? So you can apply law of conservation of mechanical energy. What has happened here, as this particle moves down, it has fallen through. When the particle is moving, the cart is also moving, right? That is true. But when the rod is vertical, from the starting point to this position, the particle has lost some gravitational potential energy. The loss in gravitational potential energy is mgl, where L is length of this rod, and that has been converted into the kinetic energy of the system. So from energy conservation, I can get this equation. There is half 6m u square, 6m, mass of the cart is 6m, it is moving with speed u. So this is kinetic energy of the cart, this is kinetic energy of the pendulum bob, that particle, half m, and in place of v, in place of this v, I am writing 6u. So half m 6u whole square. So these two kinetic energy has been produced just because of loss in gravitational potential energy of that particular particle, which is mgl. So I can get this energy equation. Now you simplify this, you will get the value of u. Hopefully I have done it correctly. U is under gl by 21. Now you get the value of u, so you know the value of v also. Again a reminder that v is equal to 6u. So 6 times of this is v. Okay, fine, very good. Now what next? What next? If I ask you a simple question, what will be your answer? I say that in ground reference frame, the particle is moving in a circle of radius l. In ground reference frame, the particle is moving in a circle of radius l. Is it true? Of course not. The particle in the reference frame of this cart is definitely moving in a circular path. But when you observe it standing on the ground, the whole cart is moving. So-called center of the circle itself is moving. So obviously it is not moving on a fixed circular path, right? So it will be a gross error if you assume that particle is going in a circle of radius L in ground reference frame. The path of the particle in ground reference frame appears to be a bit complicated. It is swinging and at the same instant this point A is translating. So a bit complicated. Okay. But in the reference frame of the cart, the motion is pretty straightforward. If there is an observer sitting inside the cart, this fellow is definitely going to tell you that this pendulum is moving in a circular path. This bob is moving in a circular path of radius L centered at point A. No doubt about it. From the very beginning itself, this observer finds that this object is moving in a circular path. So understanding motion of this object in the reference frame of the cart is much easier, right? So let us move into the reference frame of the cart. Let us think from the point of view of this observer. Now let us ask him, hello man, what is the velocity of this bob at this instant? He will say it is 7u, 7 times u, because in ground frame, velocity of this particle is 6u and velocity of cart is u. So velocity of cart means velocity of this observer is u. So this observer himself is moving with velocity u, and this bob is moving with 6u. So for him, this bob is moving at a speed of 7u, isn't it? So in the reference frame of the cart, this observer will definitely tell you that this particular particle is having a speed of 7u for this man, and he will say that it is moving in a circle centered at point A having radius L. इस आदमी के लिए पार्टिकल सर्कल में चल रहा है. At this there are many things that needs to be understood in this question. Maybe some of you would have got the answer by now, but have you thought on these points? Please listen to me. Have you thought on these points? At this particular instant, when the rod is vertical, at this very moment, the reference frame of the cart is inertial reference frame. I cannot say in general this is inertial reference frame. When the pendulum is here, somewhere here, at that instant, this rod is exerting a horizontal force on the cart, and the cart is accelerated. So this particular observer is in accelerated reference frame. He or she is in non-inertial reference frame. But at this instant, when the rod is vertical, as I told you in the very beginning, that rod cannot exert a lateral force, a perpendicular force on anything. I mean this particle as well as this support. So the rod can only apply a tension force, right? Or it can push also if required, but it will apply a force along its length only because it is a massless rod. So at this very instant, when the rod is vertical, the rod cannot apply any horizontal force on the cart. Cart is not experiencing any horizontal force. There is no acceleration of the cart at this instant. When this pendulum is somewhere here, there is horizontal acceleration of the cart. But in this position, there is no acceleration of the cart. So at this instant, this observer is in an inertial frame. Perfect inertial frame, nothing problematic as such. So this man finds that this particle is moving in a circle of radius L at speed 7u. So this is possible only if there is centripetal force. What are the forces acting on this particular particle? It is mg, and it is the tension applied by the rod. Am I right? Let us call this tension as T, right? So now writing the equation of centripetal force for this motion of particle in this reference frame, what do we get? T minus mg is the net force towards center. T minus mg is net force towards center. That must be equal to m velocity square by L. What is velocity? 7u. So T minus mg must be equal to m 7u whole squared by L. So here I have written that V relative, that means velocity of bob in reference frame of cart is 7u, u is this much, so this is the velocity 7u, and writing the equation of centripetal force, T minus mg is the net force towards center, must be equal to m this V square by L. I will just erase this so that it becomes clear. So this is the centripetal force equation. So in place of V relative, you substitute this, whatever you have got here. If you do all those substitution and calculation, I am again assuming that I have done it correctly, please check. It will be 10 by 3 mg. So tension is 10 by 3 mg. Students, what have you calculated? You have calculated that when this rod becomes vertical, tension in this rod is 10 by 3 mg. Now again think about the cart. Just think about the cart. Forget about the bob. This cart. Tension in the rod is 10 by 3 mg. So this rod is pulling the cart downward with this force. Weight of the cart is 6 mg. So what is the normal force applied by the floor? Normal force applied by the floor on the cart is T plus 6 mg. So doing T plus 6 mg will give you the answer where T is this much. So this is the force applied by the floor on the cart or cart on the floor when the rod becomes vertical. So students, I hope you have learnt n number of concepts in this discussion.